take you through the path that we had, trying to understand the sunflower conjecture, and then how we found that probabilistic processes are useful for us to do that, and then how a better understanding of these probabilistic processes helped other questions like the Kahn-Kalai conjecture and other questions. So I'll tell you what the plan for for my talks are. So again, so the title is going to be From Sunflowers to Thresholds. And is this writing too small? Is it fine? People in the back, can you see it? Yes? Sort of? OK. I'll try to write bigger. OK. And there are going to be 5 topics. So the first what I'll talk about today is just going to be about the sunflower conjecture. I mean, what it is, what are the relevant definitions, what people know about it, what are the basic things that we know and we don't know about it. OK. And then tomorrow, I'll start telling you about how to get improved bounds. And this will tie into a probabilistic process that we're going to analyze that will turn out to be very important towards understanding this problem, although initially it was very unclear why this is useful. And this in particular will use a notion of pseudo-randomness that's going to play a very important part in these 5 lectures called spreadness. So again, I'll explain everything about it tomorrow. But again, this is a notion of pseudo-randomness that plays an important part in this of developments. And then on Wednesday, we're going to prove what is going to be the main technical tool allowing all of this machinery to work, which is what's called the spread lemma. OK, so now this is to finish our proof of the sunflower conjecture and all of this machinery. But then we're going to see what else can we get from this machinery. And the next one is to be a very remarkable development, resolution of the proof of the Kahn-Kalai conjecture. By Jinian Park and Pt.1 Pham. And we'll see how they took these tools that initially we developed towards one goal and used them to solve a completely different problem that in hindsight seems very natural, but a priori was not so clear. And then the last one, the last day, I'm going to give you some aspects of how these things are used in computer science, or CS applications. I'll talk about one application in particular, how these tools have been used to prove what's called monotone circuit lower bounds. So again, so that's a plan. So let's begin. So maybe the first order of business is to say what is even a sunflower. So a sunflower is a very basic combinatorial notion that came up in the works of Erdos and Rado in the 60s. So what is a sunflower? So let's say the parameter K. A K sunflower is a family of K sets, family of K distinct sets. Let's call them S1 up to Sk, that have the same pairwise intersections. Same pairwise intersection. So what do I mean by that? There are 2 ways you can think about it. One way is just to write that Si intersected Sj is the same for all I not equal to j, but maybe this is not so intuitive. So a better way to do it is by picture. So here's the sunflower. So you choose some elements, which is going to be called the core of the sunflower. This will be the common intersection of all the sets in the sunflower. So let's say K, I'll use to denote the common intersection of all the sets in the sunflower, I from 1 to small k. And so sunflower, so you can think about the sunflower, there's a common core, maybe there's some elements here. And then there's each one of the other sets might contain a few other elements. So that's another set. This is another set, and maybe here is another set. So this is a sunflower. So sunflower, again, you have some elements that belong to all of the sets, and otherwise, the set is disjoint. So again, we have this intersection, this common intersection. So we can say that all these sets, S1 minus K up to S small k minus K. Actually, we use R, because I just want to be consistent with my notes. I'm going to try to use the same notation as in my note. We use R here for the sunflower. So R disjoint sets. OK. R up to SR minus K are all pairwise disjoint. OK? OK. So this is a sunflower. By the way, we don't have any constraints that the intersection is not empty. So this is another sunflower. Okay. That's also a sunflower with an empty intersection. Okay? And the basic question that people have been trying to study, since this was defined by Erdos and Rado in the 60s, is a Ramsey question. If I give you a family of sets, at what point is it guaranteed to contain a sunflower of a given size? Okay? And we'll see that this question turned out to be very, very important. It turned out to have a lot of applications, both in mathematics and in computer science, and it led, just studying this question, led to a lot of developments in different parts of mathematics. So just one thing before we start. So the case of R equal to 2 is trivial because every two sets form a two sunflower, right? So it's not interesting. So the first interesting case, so R equal to 3 is the first, interesting case. And we see that even for R equal to 3, there are many things that we still don't know. Even just asking, I want 3 sets that says that, except for the common intersection, they're otherwise disjoint. Even there, we don't know everything. So, OK. So what we're going to ask is the following question. And where is the eraser? Oh, here. So we're going to ask the following sort of informal question. How large can a family, let's say F, of sets be without containing a sunflower? Okay, so I need to quantify it a bit. So let's say put here an R sunflower, so some parameter R. Sunflower with R sets, R petals. Now, the question, the way I pose it now, there is no, it's sort of meaningless because you can construct an infinite family of sets with no 3 sunflowers. In fact, for those who are doing the exercises, the first exercise for today is going to be to construct an infinite family of sets without a 3 sunflower. So to get any finite bound, we need to put some restriction on the family of sets. And we're going to see that there are 2 natural restrictions. You either limit the size of your sets, or you're limiting the size of your universe. And those lead into 2 different questions. So the first one, which is the original one by Erdos and Rado, again, I'm going to try to use the same notation I have here, is that we're going to assume that, all sets have size at most n. So we're not going to limit the size of the universe, but we're going to say every set in my universe has size at most n. Okay? And we're going to mostly be focusing on this setup for these lectures, because as we're going to see later today, this is a more general setup. The other setup is by Erdos and Rado, where we limit the universe size. Universe size. So we have sets of some unbounded size, but out of n elements. And both lead into interesting questions, but we're going to see today how this question is probably harder than this question. Okay? So that's one of the things we're going to see today. So let's first make a definition. Let's focus on this Erdos and Rado setup. Check the time. Okay. So just one piece of notation. When I write an n set, I just mean a set of size n, right? A set of n elements. So let's make a definition. Let's call this SF for sunflower, NR. So that's going to be the largest size of a family of n sets that does not contain an R sunflower. Right, so this is the trivial question here. What's the largest size of a family of sets, each of size n, that does not contain this pattern of a sunflower with R sets? And basically, our main object of study for today and tomorrow and Wednesday is going to be try to prove good bounds on this set. By the way, an equivalent way of viewing it is that every family of this size plus 1 must contain a sunflower. So it's the same thing. OK. And the first thing that we're going to see is this lemma. So this was proved by Erdos and Rado in the 60s, and said that there is some, you can prove some bound on it. Maybe not a tight bound, but you can prove some bound. And the bound that we're going to see now is the following bound, which is at most, let me start with proving an upper bound or a lower bound. Let's see. Actually, let's, OK. I'll tell you the lemma. We're going to prove it in a few minutes. So the lemma is going to be n factorial r minus 1 to the n. So there is some bound you can prove, and we're going to see the proof in a few minutes. But maybe before proving it, let me show you that in fact, you can build pretty large sets without sunflowers. And I think that's going to give you some intuition why we expect this size of the sets to at least be exponential in n. So this is bound. If you think, in general, you should think about r is equal to 3 or some constant. I mean, that's the regime we will mostly be interested in, small r. So as a function of n, this behaves like n to the n, roughly. That's the order of magnitude. And I just want to show you, before we prove this, why you can find exponential in n families that do not contain a sunflower. And I think seeing these examples is very instructive to understand what's going on here. So maybe before we're going to prove this lemma, let me show you the following claim, which is a construction, which you can construct pretty large sets with unsunflower. This is also from this Erdos and Rado paper. So they have this construction, they have this lemma. So you see these two, if R is large and N is small, these are pretty similar to each other. But in the regime where R is small and N is large, this is exponential in N with some fixed bases, and this goes like N to the N. So while they seem similar, they're not quite the same thing. And then this leads to the question, like, what's the right answer? But let's first see these two bounds. So how do you construct a family of sets without a large sunflower? So here's going to be the idea. So I'm going to think of my universe in such a way. So I'm going to create a grid. Where you have n rows and r minus 1 columns. That's going to be my universe set. And my sets are going to be chosen by choosing one element in each row. Okay? So if we want to define it with formulas, if we call these rows R1 up to Rn, then the size of Ri is R minus 1. You have, and then R1 up to Rn are n disjoint sets of size R minus 1. And my family is going to be all these sets, such that for every I, the intersection with Ri has size 1. Okay? So this is my family of sets. So I want to prove two things about it. First of all, it has the right size. And second, it does not contain an R sunflower. So verifying the size is easy, right? So I choose one element in each set. So the size of my family is exactly R minus 1 to the power n, right? Everybody see that? OK. So the other question is, why does this set system or this family not contain an R sunflower? And basically, the answer is going to be because of pigeonhole. So let's see that. So let's assume that F contains an R sunflower, and we'll reach a contradiction. So let's call this S1 up to SR. And let's look at the intersection of this sunflower with just the first row of this matrix. Okay, let's look on S1 intersected R1 up to SR intersected R1. So this is still going to be that all the pairwise intersections must be the same. So there could be two cases. Either they are all the same. Right, that's one option of them all being the same, or all the intersections being the same. Or they could be all distinct. Right, these are just sets of size 1. So the only way they can form a sunflower is they're all the same or all distinct. Well, if they're all distinct, that's impossible because we have R sets here, and we chose each row to have size R minus 1. So they cannot all be distinct, so they must all be the same. But then this holds for like all the rows. So in fact, you know, S1 has to be equals to SR. So this is just R identical sets. So we don't have a sunflower. Okay? A sunflower needs to have R distinct sets. Okay? So this finishes this proof. So we gave a construction of a family of pretty large size without a sunflower. Any questions on this? In general, if you have questions, I mean, please ask them. This is supposed to be, you know, interactive as much as we can. So please stop me and ask whenever you have any questions. So we got this bound, this construction, and then the sunflower lemma that Erdos and Rado proved showed that this is not too far from the best possible. So the next step is I want us to prove this Erdos and Rado lemma. And the proof is going to be by induction. So what should I erase? Maybe actually I'll erase this part here. So finish with this construction. And by the way, we are going to see similar constructions come up at various points throughout this lecture series, where you have this matrix and some intersection with rows, and those would sort of give interesting lower bounds to various results we're going to see here. OK, so we want to prove this lemma, and the proof. Now we're going to prove this. This is, by the way, this is called the sunflower lemma. So if you look at the literature, if you read about it, when people talk about the sunflower lemma, they're talking about this lemma. So the proof is going to be basically by induction on n. So proof is going to be by induction on n. So if n is 1, n is 1, you have sets of size 1. How many sets can you have without an R? How many distinct sets of size 1 can you have without a sunflower of size R? R minus 1. Because once you have R sets, then you choose R distinct sets, they give a sunflower. So for n equal to 1, the answer is 1. R is just R minus 1. So now let's look on a larger n. And the idea was to be the following thing. So we could say, well, let's try to find as many pairwise distinct sets in my family as I can. So let S1 up to Sm in my family be the maximal number of pairwise disjoint sets. So I'm just going to try to choose sets one by one until I cannot find any other set that's disjoint from all of them. So what can we say about these sets? So one thing we say that M has to be at most R minus 1. Why? Because if I can find R pairwise disjoint sets, they form a sunflower with an empty intersection, empty common intersection, right? Otherwise, S1 up to SR form an R sunflower. Okay, so we found at most R minus 1 sets that no other set can be disjoint from all of them. So this means that every set in my family must intersect the union. Right? If you take the union of all these sets, some set in my family, like every set in my family intersects the union. So if I take, let's say, A to be the union of these sets, then this intersects all sets in my family. So in particular, it means that one of the elements in A must be very popular. It must be in a large fraction of sets of my family, right? So some element, I know, A in A must be in at least, the size of my family over A. Many sets in F, right? One of these elements must be popular. So now we're just going to restrict to all the sets that contain this one popular element and remove it. So let F prime be take all the sets in my family that contain this element and remove it. Right, so I have this popular element A here, and it's in this set, and it's in this set, and it's in this set. So we're just going to take all of these sets and remove this one element. So I claim two things about this F prime. So first, a few things. So first of all, F prime is a family of sets of size n minus 1, because F was a family of sets of size n. And now we remove one element, it's n minus 1. So that's obvious. So the second thing that might not be obvious is that F prime also does not contain an R sunflower, okay? Which is why now we can use induction. So let's see, why is this F prime not containing an R sunflower? So let's see why. So assume maybe S1 prime up to SR prime in F prime form an R sunflower, right? So we have some common elements, and then we have sort of this pattern. So this is one set, there's a second set, there's a third set. So now we can just add A back to them, to all of them, and get a sunflower in my original set system F. So if I choose Si to be Si prime union A, so we remove back the element that we add back the element that we removed before, then S1 up to SR are in F, and they're a sunflower. And we assume that, no, we cannot have a sunflower. We assume that our set system does not contain an R sunflower. So again, what's the idea here? We choose an element that's popular in many sets. We remove it. We only keep these sets. Now we get a set system on with sets of one less element. It still does not contain an R sunflower. So now we can use induction, right? So now we can say, well, what can we say about the size? So the size of F prime by induction is at most whatever bound we have for set of size n minus 1 R. And we said that the size of F prime here is at least the set of F over how many, like the set of A, just the union of all the disjoint sets you could find. We have at most R minus 1 of them. So you put everything together and you get the bound. So let's just do the calculation. Okay, so we just get that sort of the size of F is at most the size of A times the size of F prime, which is at most, we have at most R minus 1 sets of size n. And now we can just plug in inductively the bound that we had before, which was n minus 1 factorial R minus 1 to the n minus 1. Here you just apply the bound inductively for n minus 1, and we get exactly what we want to get. N factorial, R minus 1 to the n. Okay, so this finishes this sunflower lemma proof. But again, even if you got lost in some of the details, the basic idea is very simple. You say, I'm going to say that there cannot be R pairwise disjoint sets, otherwise they form a sunflower. There are at most R minus 1 of them. So one of the elements in them must be popular. It must belong to many sets in the family. Just take these sets, remove this element, use induction, and do the calculation. Okay, that's a proof. Okay, so it seems like a very simple proof, and we also have a very simple construction, and they almost match. And now the question is, what's the right answer? So Erdos and Rado made the sunflower conjecture that said that they suspect that the lower bound is probably closer to the true answer. And I think one of the reasons they made this conjecture is because this upper bound is sort of very simple, right? So we're not really using a lot of the structure here, so they were hoping that maybe you can sort of improve it. So the conjecture was the following, which is the maximal size of a family of sets of size n without R. And again, this is in the regime where R is small and n is big, is at most some constant that depends on R to the n. So it is an exponential in n where the base is if R is 3, the base is some constant, not dependent on n in any way. Okay. And by the way, this is still open. We still don't know it, even for R equal to 3. Right? So this is open even for R equal to 3. So if you want some question to think about to do this week, you can always try to prove it by the end of the week. That would be very nice. Good. So let me tell you what we know about this conjecture. So I told you two facts already, that we have a construction that is not that this is already exponential. We have the sunflower lemma. What else do we know? Because this is from like 1960, and it's been like, what, 65 years since that. Okay, so what's the status? So again, we have a construction showing that this side of the largest family without sunflower is at least R minus 1 to the n. We've seen that. And we also have the sunflower lemma. That's right, like SF lemma. again, both from the 60s, showing that this is not too far off the best you could hope. So this is again, both of those are from 1960. What afterwards? So there's work by Kostochka from 96, where he improved a little bit the upper bound. So he showed, again, for fixed R, if R is some constant, he improved the upper bound to at most. So this is about n to the n. So it's something like n to the 1 minus little of 1. So he improved by a little bit the exponent. That was the first improvement. And then it took another 20 years. So Fukuyama in 18, for R equal to 3, improved the bound to something like n to the about 3/4 n. So improved the exponent from n to 3/4 n. And then we had the work a few years ago. So this is with Ryan Elweiss, myself, Kewen Wu, and Jiapeng Zhang. And again, this is, so we originally studied this question because it had some connections to some other problems we cared about in complexity theory. But then we realized that we can use techniques coming from complexity theory to try to prove better bounds on it. And the bound we could prove was something like the following. Some constant R log Rn to the n times some load of terms, like log n to the order n. Okay. So this is the main term here. And again, if you think about R as constant, then this scale is like log n to the n instead of n to the n. So this doesn't sort of solve the conjecture. It's not a constant to the n, but the base was improved from n to log n. But then we had this sort of annoying, stuff, these terms that we thought shouldn't really be here because, it's something that just comes from the analysis. But in fact, this was the case. So after we had this works, and several people have sort of, reproved it using different techniques and improved the bounds in different ways. So maybe the first significant improvement was by Frankston, Kahn, Narayanan, and Park. This is from 21. They improved the bound to, they cleaned all this off. They found a way to clean up a lot of our analysis and improve the bound to just be, some constant R log Rn to the n. Again, C is some absolute constant, I don't know, 20 or something. And in fact, they use this, their main motivation for studying this is because they realized something, that they can use the techniques that we had in the analysis to prove another question that seemed to be completely unrelated. So they proved what's called the fractional Kahn-Kalai conjecture, which I will not tell you exactly what it is in this lecture series, because later on we're going to see a proof of the full conjecture. But this is there was some conjecture by Kahn-Kalai about random graphs and threshold phenomena in random graphs. And then, because it seems hard, and later Talleyrand came up with this fractional relaxation of it, which is called the fractional Kahn-Kalai conjecture, which is actually by Talleyrand, from what I know. Anyway, so they were able to solve it using these techniques. And then there were like reproofs using information theory. So just taking these proofs that were more combinatorial and recasting them in the language of entropies and information that made some parts of the proof more streamlined. So this is by Anup Rao and Terry Tao, and I think there were a few other ones. And, OK. OK, so we had this bound that seemed pretty good, seemed pretty close to tight for this type of analysis. But in fact, it was like one more advance. So Bell, Chueluecha, and Warnke. So this is again in 21. Improved the bound even more. So they were able to clean one more part of the analysis and improve some constant R log n to the n. And in fact, they did it as part of an REU project. So I think all of them, or at least 2 of the 3, are undergrads, and this is part of an REU project that they did over the summer. So improving the analysis even further. And this is where we stand. This is the best that we know so far. And we also know that this is the right answer for this type of analysis. So what we're going to see tomorrow and on Wednesday is that the technique that we developed here proves something stronger than just sunflower. They find a structure that seems to be more structured than sunflower, that guarantees sunflowers, but it is sort of more powerful. And for this more powerful structure, this is the right answer. So at least for this type of techniques, that seems to be the limit. But there's one more twist here, which is Park and Farm. Last year, basically, they extended the techniques and they proved the full Kahn-Kalai conjecture. And it's a beautiful proof, and it really sort of identified that some of the elements of this proof that we're going to see tomorrow on Tuesday and on Wednesday can be sort of, move to regimes that seems to be where you have no assumptions, no sort of assumptions. And I'm going to show you the full details of that on Thursday. So you're going to learn what is a Kahn-Kalai conjecture, why it is an important conjecture, why it seemed originally very unbelievable that you can prove it, but then why it is in fact true. So we're going to see all of that on Thursday. OK, so this is all in terms of status. There's one more thing I wanted to tell you about today. So I told you that there's these 2 regimes that people have studied. So the one we studied so far is this Erdos and Rado setup, where you limit the size of sets in your universe. But there is a different setting that also comes up in some applications where you don't limit the size of the set, but you limit the size of the universe. And I want to show you what do we know about this and why this is, in fact, a special case of this Erdos and Rado setup, like how you can reduce formally from one to the other. So this is the last thing I want to show you today. So Erdos summary sunflowers. So let me denote by ES for Erdos summary. If now we use capital N for the size of the universe, and R, which will be the largest size of a family F of sets S inside some universe of capital N elements. So this just means the numbers 1 to 3 up to n, but just any set of size capital N, again, without an R sunflower. Okay? So again, it's the same type of equation, except here we're not limiting the size of the sets. We are limiting the size of the universe. So typically, you want to think about sets of size that's pretty large, let's say linear in capital N. Right? If they're too small, there will be not enough sets there. So first, let me show you how you can construct, again, like we saw the construction of a large family of sets without a sunflower when you have all the set of size small n. Now I want to show you a similar construction that works in the regime where you limit the set of the universe. Okay. So again, we're going to think about the regime where R is small and capital N is big. But just to gain some intuition, one of the exercises for the students who are taking the exercises is going to be to analyze this case where if I have sets of size R and I want, R minus 1 R, meaning I want to have all families, all subsets of size of a universe size R minus 1 without an R sunflower. So this is actually going to be something that you can directly analyze. It's going to be 2 to the R minus 1 minus 1. So it's all the sets except for 1. So again, this is just an exercise to get some intuition. I mean, the interesting regime is when this parameter is big and R is small. So this is just as an exercise. OK. So the thing I want to tell you about is this claim that sort of, again, let's think about R fixed and N large. That we can construct a family without an R sunflower of size what? Well, let's see. All of the sets here are going to be size 2 to the n. That's everything. So it should be so it's slightly less than that. It's going to be at least 2 to the 1 minus epsilon n, where epsilon depends on R. And concretely, it sort of scales like log R over R. Okay? So as R gets bigger, we can construct larger and larger families without an R sunflower. But we never get to the full 2 to the n. Because it is the construction, we'll just lose some constantly depending on R. And later we're going to say conjecture, this summary of this sunflower conjecture that says that this should be the right answer. But let me first show you, at least sketch this construction. And the construction is going to be very similar to the previous construction, but with some modification. So what's going to be the construction? So it's going to look very similar. So we're going to choose a matrix here of size. So here's going to be R minus 1. Now you want to have total capital N elements in the universe. So here we're going to have capital N over R minus 1 sets. So let's call this number M. So we have R1 up to Rm. OK? And the construction, let's have the construction. The construction is going to be all the sets that have half the elements in each row. Okay? So that for every I, S intersected Ri is of size exactly R minus 1 over 2. Let's say, round it down. So for the sake of time, I'm not going to analyze this here. We have the analysis in the notes, which I think are available on the website or are going to be available soon. Or you could do this as an exercise if you want. So, but in this construction, you can use an analysis similar to the one we did before and prove, first of all, that it does not contain an R sunflower. And second, these are now pretty big sets. So the side of this family, just to see why you get the right size, what's the side of this family? Well, in every set of size R minus 1, we choose a balance that of size half the elements. So it's going to be R minus 1 choose R minus 1 over 2 to the power n over R minus 1. And this is only 1 over R or 1 over root R compared to 2 to the power R minus 1. So this is about going to be 2 to the n times 1 over root R to the n over R minus 1. And if you do the analysis, you get 2 to the 1 minus epsilon, where epsilon has this scaling with R. So I won't do the calculations here. I think it's a good exercise to do if you want to. So we can still get pretty large sets without sunflowers. And after again, what should be the right answer? So they came with the following conjecture. So the conjecture here is that the right answer should be the same as we got for this construction. 2 to the 1 minus epsilon n for some epsilon that depends on R, right? Some positive epsilon depending on R. That is a sunflower conjecture for this Erdos-Rado setup. So again, we have a construction, and the conjecture says this construction is essentially the best we can do. Maybe we can improve constants, but nothing beyond that. And very nicely, this is known for R equals to 3. So, there was this famous resolution of the cap set conjecture a few years ago using polynomial methods, and using the same techniques, you can prove the first case of this Erdos-Rado setup of R equal to 3. And many people were hoping that maybe we can use these polynomial methods to also resolve the other cases of it, or maybe the full sunflower conjecture. But so far, nothing has worked. So far, we don't know how to use these techniques to prove even the R equal to the 4 case. It's not that we know that they don't work. We don't know if they work. We don't know if they don't work. There's a lot of mystery around it. But these techniques are polynomial or method techniques. They're algebraic techniques. They're going to be very different to the techniques I'm going to tell you about in this series lecture. So I won't tell you anything about this proof, but I'm assuming that many of you have heard about it, and if you haven't, you should read about it. There are many good lecture notes online on this of cap set and the R equal to 3 case. And I think one of our exercises is actually giving a direct reduction from the cap set question to the R equal to 3 question for sunflowers. Yeah, one of the questions in the exercises. So the last thing I want to do today, and let me just check how much time I have left. I have like 11 minutes left. Okay, so the last thing I want to tell you today is why is this Erdos-Rado setup really more general than the Erdos-Rado setup? Because at face value, they might look just two incomparable setups. One, you limit the size of the sets. The other one, you limit the size of the universe. So I want to show you why you can formally reduce one to the other. Okay, that's the last thing I want to show you today. Okay, so the lemma I want to show you is that the Erdos-Rado sunflower conjecture implies this Erdos-Rado sunflower conjecture. Okay, so if you could get the conjecture bound for families where all the sets have bounded size, you get the same thing for the bounded size of the universe. So let's do that. So proof. So we want to prove the Erdos-Rado sunflower conjecture, assuming, of course, the Erdos-Rado sunflower conjecture. So again, so let F be a family of sets in N without an R sunflower. And our goal is to prove that it is exponentially far from maximal, 1 minus epsilon n, for some epsilon that depends on R. That's our goal. Again, assuming the sunflower conjecture for the Erdos-Rado sunflower conjecture. So the first thing we're going to do is we're just going to simplify our lives and restrict all the sets to the most popular size. So let's S be the most popular size of sets in F, and define F1 to be all the sets in F that have size small s. Okay? So because it's the most popular size, we know that the size of F1 is at least 1 over n plus 1, the size of F. There are only n plus 1 sizes. So if we can prove a bound, and sorry, this should be capital N. if you can improve a bound like that, saving something exponential for f1, it's going to give us the same bound, more or less, for f as well. Maybe slightly worse epsilon. So we can just restrict on f1 for now. Okay? The other observation we can take is that S has to be somewhat close to n over 2. If S is too far from n over 2, we are done, right? So we can assume S to be, for example, in 0.4n to 0.6n, the most popular side. Otherwise, if not, then we can limit the size of f1 by at most n choose, let's say, 0.4n, which is, 2 to the 1 minus epsilon n, for some epsilon that's positive, right? So we can assume that the most popular size is somewhere close to half, which makes sense. Good. So one thing you might want to do directly is say, well, maybe now we have a family of sets, all of the same size S. Maybe we can just directly apply Erdos and Rado. So we're going to try it, we're going to fail, and then we're going to see how to fix it. So first attempt will be to apply Erdos and Rado directly. Right? So we have a family of sets of size S. So we could say, well, the size of f1 is at most some constant to the S for some constant that depends on R. This is what the Erdos and Rado sunflower conjecture tells us. That no, if you have a family of sets of size S without an R sunflower, there's some exponential bound on the side where the base just depends on R. But I'm claiming this is sort of meaningless, right? Because S is close to n over 2. Imagine S is n over 2. If C is 4 or something, then we get nothing, right? So this is sort of meaningless. Meaningless if, say, C is at least 4. So we cannot just apply directly. We get two loops of a bound. So we have to do some extra processing on top of it. And the idea that's going to make it work is to say, well, let's not take all the sets, but take all the sets with the same common subset inside them, and then remove it. Okay? So let me tell you how to solve it. So let's say M to be some parameter that's going to be, think about as delta S, that's going to fix later. M is some small fraction of S. Okay? We're going to fix M later. And we're going to choose a set I of size M minus S. Sorry, S minus M. And we're going to take F2 to be all the sets in F1. Sorry, all the sets in F1 that contain I as a subset. And we're going to remove it. S minus I. Okay? Yes?
And this S is the same as that A?
S is, so we have this parameter S, which is a typical, sorry, delta S. M is a parameter for now. M is going to be something much smaller than the size, okay? Okay. And we're going to choose I, some set I, that's going to be, so we have families where all the sets have size S. And we're going to choose a set that's slightly smaller, size S minus M, I, and we're going to take all the sets containing I. And then we're going to remove I from them. Okay? So this is going to be F2. And we're going to choose I so that we're going to choose I that's the most popular. Meaning we're going to choose a set I of size S minus M that is containing the largest number of sets inside F1. Okay? So what can we say? First of all, F2 is now a family of sets of size M, right? Because we took set of size S, we remove a common set of size S minus M. Now we just say, so we can say, now we can apply Erdos and Rado to F2 directly. Say F2 is of size C to the M. And because M is now a free parameter for us to play with, that's going to be enough, good enough to battle against this constant C might be large, more like 10 or something, right? So, but now let's just finish the calculations. So F2 is, we have this bound. This comes from the Erdos and Rado conjecture. And now I want to relate the size of F2 to the size of F1. So we're just going to use averaging. So we say, well, how large can F2 be? It's going to be at least the average size of it if I choose I randomly, right? So we can say the size of F2 is going to be what? So every set, let me think what the easiest way of doing it. Let me just write it and explain. So we get this bound relating F2 and F1. So why is this the case? Well, imagine choosing a random set of size S minus M. What's the probability it is contained in a set inside F1? The total number of sets of size S minus M is this inside the universe. But every set of size S contains that many. So this is just going to be the expectation. So this is what shows I randomly. So of course, the maximum is going to be even more than that. And then, if you do the calculation, we're just going to say this is at least going to be, S choose M. This is just going to simply bound by 2 to the n times F1. Okay? So we say this set F2 is not too tiny compared to F1. And for F2, we have a bound that is just exponential in M. So now if you put everything together, and I'll do it here in a minute, it's just going to give us the bound that we want. So the main trick here that made this work is that we don't apply Erdos and Rado directly to the family that we get by getting the most popular side. It will be also restrict to many sets that contain the same common subset, and we remove it. So we get a much smaller set of sets. So this was a trick to make it work. So let's just finish the calculation, then we'll be done for today. So let's just put everything together. So the size of F is going to be at most n plus 1, the size of F1, which is going to be n plus 1 times 2 to the n over S choose M, the size of F2. And here we're going to apply the Erdos and Rado setup. So this is going to be, again, I'm going to put this 2 to the n outside. This is what we're going to fight against. Again, n plus 1. And then here we're going to get C to the m over S choose M. Right? And remember, we're going to choose M to be something like a small fraction of S, some delta fraction of S. So this, again, this n plus 1 doesn't really matter much. This is approximately 2 to the n times, what do we have here? Some constant to the m over delta choose m, because, again, m was like a delta fraction of S, so S is m over delta. And this is about 2 to the n times C delta to the m. So if we choose delta to be some fraction that is small, if we choose, for example, delta to be, I don't know, if we choose delta to be 1 over 2c, then this is, so S, the size was like something linear close in n, close to n over 2. This is still something linear in n. But now the proportion delta depends on whatever constant the Erdos and Rado conjecture happens to give us. And this gives us, again, an exponential saving. Okay? So again, even if you didn't follow all the details here, the high-level idea that you can take a family of sets in a universe, restrict to one of popular side, restrict to the ones with the same common intersection, remove it, now we get small sets, we can apply Erdos and Rado directly. So this proves that this Erdos and Rado framework is indeed formally more powerful than the Erdos and Rado one. But again, unfortunately, even though the Erdos and Rado one is sort of simpler, it's only known to be true for R equal to 3, the first case. I think this is a good point for us to finish for today. And just again, so if you want to do the exercise, we have several exercises related to these notions that are going to come up. And what I'm going to start talking about tomorrow is about our approach of using probabilistic methods to try to attack this half-flower conjecture. Okay, that's it. Thank you.